Okay, so in 6.2, we're going to start with just kind of a review of proportions and look at a bunch of equivalent proportions and different properties that we can do. And we have two fractions set equal to each other. And then we're going to look at some applications as it pertains to geometry and triangles and all that good stuff. So first of all, the most basic proportion property that we know is we can cross multiply. So the product of the extremes is equal to the product of the means. That's a really mathy way of saying that if you have A over B equaling C over D, that means that AD is equal to BC every single time. And that's how we solve proportions. That's something we're familiar with. That's stuff we did back in 6.1. But what might be interesting is that reciprocals are always equal in proportion. So if you have A over B is equal to C over D, then that would also have to mean that B over A is equal to D over C, where you just kind of flip-flop numerator and denominator. It's actually easier to see with actual numbers, so I think we can all agree that 3 over 6 is equal to 12 over 24. They would both reduce just to 1/2. But if you flipped both of those fractions and did the reciprocal, 6 over 3 is equal to 24 over 12. That's also true. They're both equal to 2. And that's going to work for any type of true proportion. Similarly, you can always interchange the means. What that means is you can swap the two numbers that are diagonal from each other, or the expressions that are diagonal to each other. So for example, I think we can all agree that 2/5 is equal to 4/10. They're the same fraction, they're written differently. But if we flip these two numbers and write, instead of 2 over 5, write 2 over 4, that is equal to 5 over 10. Now, this isn't saying that 2/4 is equal to 2/5, but it's just saying this is still a true proportion because 2/4 is equal to 5/10. That's kind of crazy. So P over 6 is equal to R over 10. That would mean that P over R is equal to 6 over 10. And none of what we're going over right now is groundbreaking stuff. It's not going to change anything you're doing. It's not like a rule. It's not a formula. It's more of a just because. Because when we set up these problems with actual shapes, what we're going to find out is you can set up the proportions a lot of different ways and still have the correct answer. What that means is if you're looking through like a key, like an answer key that I post, you might see me do it differently from you, and you're going to get the same answer, and that's okay. So typically whenever we set up proportions to solve, there's like 4 different correct ways to set it up. One other way we can do it, this is the last property we'll talk about before we transition into geometry, is you can actually add the denominator to the numerator of each of the top of each fraction and still maintain a congruent or equal statement with your two proportions. So for example, you would take 6 over 14 and change that to 6 plus 14, which is just 20. So 20 over 14 is equal to, add the denominator to the numerator up here, 3 plus 7, and you'd get 10 over 7. And that's also true. 20 over 14 is definitely equal to 10 over 7. Finally here you can go 3 plus x over x and 5 plus y over y. And it doesn't really make sense why we would ever need to do that. But when we see pictures, we're going to see that we sometimes like to take an entire length instead of breaking it up into chunks. So let's try one of these. This is just kind of an example proportion problem for geometry. We're given this picture. We're told that AB over BD is equal to AC over CE. In other words, AB and BD are proportional to AC and CE. So you have this long side over a short side is equal to this long side over that short side. And we're asked to find the length of BD. Well, what I recommend doing is just substituting in values where we can. So AB over BD becomes 16 over X is equal to AC. We don't really know what that is by looking at it, but you take a second look. This whole length is 10, or excuse me, this whole length is 30, this chunk is 10, so AC would have to be 20. Equal to 20 over CE is 10. From here you can cross multiply. You could simplify on the right first if you wanted. I'll just go ahead and cross multiply. That's what most of you are going to want to do. 20x is equal to 160. And then when we divide both sides by 20, you just get 8 for x. So dB is 8. I want you to get in the habit of if you're asked to give the length for BD, write your final answer as DB equals 8. Let's try another one. So here we're given another picture. We're told we're asked to find LQ given that MQ over MN is equal to LQ over LP. So let's substitute some things in that we know. MQ is equal to, well, 6 plus 15, it's got to be 21. Over MN, which is just 6. So you'll see here we're taking the entire chunk over just a fraction of it. And that's equal to LQ, which we're solving for, over LP, which is 5. Cross multiply. 21 times 5 is, I think, 105, is equal to 6LQ. From here, you can take both sides and you can divide by 6. And I think we get 17 and a half for the length of LQ. So what that would mean is if you wanted to follow that up, you could find what PQ is. You just take away 5 from LQ and you'd get 12.5 for whatever that's worth. So the last thing we're going to talk about in this video is to find the scale of a drawing. So a lot of times in the real world, we want to draw pictures that are proportional to a real thing, but maybe they're bigger or smaller. So maybe in chemistry class, you're dealing with something really small, and you want to have a scale drawing of something that's just a little bit bigger so we can actually see it. Or architects will draw out big houses and buildings, but they'll draw them on paper, and they'll draw everything to scale. So the scale of a drawing or a model is just the fraction of the model over the actual. So this is an ancient cell phone. The length of the antenna on the blueprint, we're told, is 5 centimeters. The actual length of the real antenna on the real phone is 2 centimeters. So the scale would be 5 over 2. And if we want to put units in, we can put units in. In general, as long as units are the same when you're comparing two things, it's fine. So let's look at maybe a better example. So a scale model of the Titanic is 107.5 inches long. So obviously that's a lot smaller than the real Titanic, and it's only 11.25 inches wide. The real Titanic was 882.75 feet long. We're asked to find the scale of the model and then figure out how wide the Titanic was. So the scale of the model, you're just going to compare like things. So in this case, we know the actual length. It's 882.75 feet. And the actual length of the model is 107.5. So we can simplify that if we want. We can simplify that if we want. I got to get my calculator out. So 107.5 divided by 882.75. It's not going to be a pretty fraction. You get a gross decimal. We can just leave it like that, actually. Then to figure out how wide the Titanic is, I like still setting up a proportion. So the length of the model is 107.5. The width of the model is 11.25. The length of the actual Titanic is 882.75. We're not putting units on anything. And the width can be our x. So to find the width, you can basically set up a proportion just like this, where you take 107.5 over 882.75. Set that equal to 11.25 over x. Cross multiply, kind of running out of room. 107.5x is equal to, we'll take out our calculator, we'll go 11.25 times 882.75. We get 9,930.94. Divide both sides by 107.5. And we get 92.38. And then in the context of the problem, we know our units are feet, so we would say it's 92.38 feet wide. That's basically how you can use the scale to find the length of something that's either really, really big or really, really small. And that's actually where we're going to leave off for the notes today.